Right, the last little part of functions and graphs and drawing those graphs is to just look at a few different ones. Okay, you've kind of looked at these already, and I'm just going to start by going through the ones that you have already seen, but you basically actually looked at these in National 5. Okay, so if you know a graph of a function, and obviously it can be any kind of function, it can be anything from a straight line right up to cubics and quartics. If we know that function, then we can draw the graph of these following functions. Okay, and as I say, you kind of covered these at National 5, but you've got minus f of x, f of minus x, f of x plus or minus a, f of x plus or minus b, some number in front of you k, f of, and some in front of your function f of x, and then some number in front of your x. Okay, and obviously what they all do to the graph is listed here. So you need to know these to an extent, and I'm going to look at a couple more in a bit more detail. But as I say, these you covered in National 5, and you obviously redid in higher. So you should hopefully know all of these by now. But there's a list nonetheless. Okay, but we started looking at this to an extent in higher, but you didn't do a massive amount of it, and we're going to kind of expand on it a little bit in advanced higher. Okay, so if we wanted to draw the inverse function of a graph, we already know, hopefully, that if you remember from doing it in higher, that it's just a reflection in the line y equals x, and knowing that makes it quite straightforward to draw. Okay, so for example, if we had something like this, the graph of the function f of x equals x cubed is shown. Sketch the graph of f of x equals x cubed and y equals the cubed root of x on the same diagram, clearly marking any points in intersection. So the point is there, it doesn't actually tell you anything about the fact, anything about inverses. But by looking at this, hopefully we can recognize that x cubed and the cubed root of x are the inverse of one another. Okay, so if f of x equals x cubed, then the inverse of that function will be the cubed root of x. In which case, straight away, we know that it reflects on the line y equals x, so we can draw that, and then we can just reflect it across that line, and then obviously draw the graph of y equals the cubed root of x. But the difference comes from actually clearly marking any points of intersection. And this is straightforward enough, especially if you've drawn it in advance. You can see that there's 3 points, okay, and you can roughly work out where they are. Okay, but the idea to work out where they actually intersect is where the two lines, the two curves, are actually equal to one another. In other words, where x cubed equals x. So it's where this line, if we did it x cubed equals the cubed root of x, it's going to be a bit more awkward, but it's where y equals x intersects the line y equals x cubed. So in other words, where x equals x cubed. And then it's just a more basic equation that we can solve. We could have done it with x, the cubed root of x and x cubed, but it's a bit more complicated than we need. We can see that obviously the blue line intersects the turquoisey dotted line at the same points, so we can use those two lines, which makes our lives a little bit easier. Okay, so it's where x equals x cubed, and then it's just an equation that we can solve. Get it all to one side, x cubed minus x. Factorize x bracket x squared minus 1, and hopefully we recognize that that's the difference of two squares. So it's x bracket x minus 1, x plus 1 equals 0, in which case we have three solutions, x equals minus 1, 0, or 1. Obviously, that's just the x values, and we want to find the y values as well because we're looking for coordinates. But because we know that's on the line y equals x, then we know it's just going to be minus 1, 0, 0, and 1, 1. And we can clearly mark them. I don't think I've actually done that, but I can clearly mark them on the actual graph. Okay, so straightforward enough. Inverse functions, obviously just a reflection in the line y equals x, so it's easy enough to draw, and then it's just a case of finding where they intersect each other. Okay. Oh, I have marked them. Oh, lovely. Okay. Right. This one's slightly different. This one you haven't done before. This is a graph of the modulus of functions. Okay. So given a function f of x, the modulus function, and written like that, so the two lines either side of the f of x is defined as followed. Okay, you might already kind of work this out. The idea of a modulus is that it's not negative, okay? So the modulus of f of x is fine as long as f of x is greater than or equal to 0, okay? It'll just be consistent with what it normally would. However, if and where the graph of f of x is negative, then we have to basically reflect it. So if f of x is less than 0, then we draw the graph as minus f of x. Okay, we actually reflect that basically in the x-axis. Okay, so when f of x is greater than or equal to 0, the graph of the modulus of f of x will equal the graph of f of x. It'll just be exactly the same as normal. However, if f of x is less than 0 at any point, then the graph of the modulus will be the reflection of f of x in the x-axis. So in particular, since the modulus of f of x is always non-negative, the graph of the modulus of f of x will always lie on or above the x-axis. So there's a clue in itself. You'll never actually have to draw this below the x-axis. And if you do, if the graph of f of x is below the x-axis, then you literally just flip it over the x-axis and draw it as such. Okay, so given that f of x equals 1 over x plus 3, we're going to sketch the graph of the modulus of f of x. Right, that's the graph of f of x. That's the graph of 1 over x plus 3. But if we want to draw the modulus, then basically we reflect the part, any part that's under the x-axis, any part that has negative y's, we reflect it back over the x-axis so that it all is above the x-axis. It is all just positive. And therefore, that's your graph of the modulus of f of x.